Okay. So hello. Okay, so we come back to the class now. We have here two more cumulative distribution. So and it looks like this if you draw it on a graph. So right now you see product S and product R are not so for until 15. This is the use a different color. Until 15, so this is exactly the same case, right? R and S, R dominate S, right? So you know R is better. But if you go over 15, you see that somehow in this range, it seems like R is worse and the S is better, right? It reverses. But what really matters, so you suppose this area is even smaller. So now this area is about this size, right? And if this area is even smaller, the intuition is quite clear. Intuition is that the product R is still better than product S. But how do you actually describe that or mathematically show that? Okay, so the definition is that you do a integral from minus infinity to x, and if the difference between the cumulative function, the integral of that is positive for all x with strict inequality at some x, then we say that R is second degree stochastic dominant S. So if I can, help you recall some of your memory from undergrad calculus, the integral of a function of the difference of these two functions is simply the area in between these two lines, right? So until 15, the area is this. Okay, so we use S minus R. So now the area is positive, right? This area is, until 15 is bigger, the area is getting bigger and bigger, right? And for this range, you will get a negative number adding up to the number here. So suppose this area is some number, say, we call it the total number is area blue, okay? And this is area red. What I really need is basically blue is bigger than red. Then we will have this property. Okay? This is the definition. And are we clear about the definition? So sometimes you can actually do this calculation by your eye. Like this one is easy. You see that the R is much smaller than B, right? So you know that there is a dominance relation. But if the number is less clear, then you might need to actually run the math by hand. Okay. And then remember in the previous example, we say that that first degree stochastic means we don't care about probability. We don't actually care about the risk because Q is much more better than P. So, no matter whom you're talking to, this decision maker should choose product Q. Here we need some sort of, for you to convince someone that product R is better than product S, you need something more than saying that R is just always better than S, because that's not true, right? In some cases, actually, R can be worse. But as long as this condition, the SD hold, second degree stochastic dominance hold, then for any function U and any concave utility function U, the expected utility of product R and the expected utility of product S, non-decreasing and concave. By the way, Ben, that's why last time the midterm example, actually, I was a little bit incorrect. So you said that, you write I said concave, and what's the property of concave, right? One of the answer is increasing or non-decreasing. And actually, you can have a concave function, but it's actually decreasing. So it's not true that, you have to add this condition of non-decreasing or increasing. Okay, so for non-decreasing utility function means more is better. Getting more is better for you. And concave means what? Midterm question. Concave means what? No, I mean for this guy's risk preference. What is mean by concave utility function? Last week.
Risk aversion.
Yeah, risk averse, right? So if someone, non-decreasing is actually, you always assume non-decreasing. Okay, so that's something else. But basically, there's only one more assumption you need. You assume that the utility function is concave. That means you assume this person is risk averse. No matter how risk averse this person is, as long as he's a little bit risk averse, okay? Then because the expected utility from product R is greater than or equal to the expected utility from product S, so you can still convince this guy that product R is better than product S. Understood the difference between first order as first degree and second degree stochastic dominance? Any part that's not clear, I need to go through again. You can tell me.
You need to do both, okay?
So if you do first degree, and you find first degree hold, it guarantees second degree, right? Because here it says non-decreasing and concave utility function U. For first degree, you don't even need a concave condition. That's for any non-decreasing function U. Expected utility from R is better than expected utility from S. So first degree is stronger, basically. Second degree, you need more condition. So that's like if you go to some decision maker and he's choosing between the two distribution or two product. First, you need to check the distribution, see if it is first degree stochastic dominance. If that's the case, you don't need to know this guy's preference. You only need to know that this guy loves money. More money is better. Then you can make the decision for him or tell him that this decision is simple. If you check the distribution and found out that it's not first degree, then you can check for second degree. And if you check for second degree and found that it's actually hold, then you can ask this guy, whether, or check this with this guy whether he's risk averse or not, or does he has a concave utility function, which we already taught how to do that, right? So after you get his utility function, you can see whether this guy is concave, is risk averse and has a concave utility function. If he does, then again you can make the decision for him or tell him that the decision is easy. Clear? Not clear? Any part that I need to state again? No?
Just to make sure, if he's not risk averse, we cannot choose 7 degree.
We cannot say that, suppose for example, he is risk neutral or even risk loving, then we cannot say that R is better. Yeah. I'll go back to this later. Everybody know what's normal distribution, right? Bell function, okay, bell shape. Okay. Now, suppose we have two different utility functions. Both are quadratic. Quadratic means the power of x is up to 2, okay, or exactly 2. So it will satisfy our condition for concave utility function. Okay, so for example, if you don't know how to set up a concave utility function, you can assume excuse me. You can assume a quadratic form. Okay? And suppose you have an annual cash inflow for the two machine, alpha machine and beta machine, for the year 1, 2, 3, 4 as follow, inflow and outflow. How do you, here we're going to talk about another thing. So we talk about something called the net present value or present value. Does anyone here don't understand why we need something called the present value? Or for those who understand what is present value, can you raise your hand? So only you, I guess. Okay. So the idea of present value is kind of easy. So the $1,000, so I give you $1,000 today. That means you get $1,000. But if I give you $1,000 100 years later, that's totally not worth to you for you today. That doesn't worth $1,000 because if you have $1,000 today, you can save it to the bank. And although the interest rate right now is basically 0, but suppose the interest rate is even just 1%, then after 72 years, it will double and become 2,000. Okay? So after 100 years, actually even more than double. So 1,000, that means 1,000 year today worth 2,000 something dollar 100 years later. And that means 2,000 something dollar in the future worth to you $1,000 today. So that means $1,000, in the future, 100 years later, doesn't worth $1,000 today. And how do we actually calculate that? So, he uses the the text will use something called the present value factor to do the calculation. So for now, everything is associated with a present value factor of 1. For 1 year from now, everything is associated with a present value factor of 0.9. That means $100 for me from a year from now only worth to me $100 times 0.9091 today. Okay? So now this is $100 from a year times 0.9091. It becomes excuse me. It becomes 90.91 for now. That's how you calculate it. Are we clear? What it means by present value factor? Okay? And you might have earned this in an accounting class or economic class, that there is a more formulated way to do this. So you assume that the interest rate is R. Then $1 tomorrow will be, what a year from now will be, the yearly interest rates are. Then $1 tomorrow, today will be 1 plus $R tomorrow, right? So $1 tomorrow will be 1 over 1 plus R today. Not today, next year, so 1 year. So basically that means this factor is basically 1 over 1 plus R. And this number is 1 over 1 plus R to the power of 2. This number is 1 power R to the power of 3. And so on. Any part not clear, confused? Do you guys understand what I'm doing here? Okay? Okay? So this is how, if there's no uncertainty, this is how you do it basically. So year 1, the inflow is this, outflow is this. So net cash flow is this. And you times the present value factor, it becomes this number. And you add them all. Then the net present value is 1,542. Okay. And this is for the beta machine, just a different machine. Okay, the same thing. And suppose now you introduce some randomness or uncertainty. So now you have probability distribution for alpha machine and probability distribution for this is distribution only for alpha machine actually. Yeah, okay, so for year 1 the revenue is distributed this way. Year 2, year 1 the maintenance cost is this way, and so on. Okay, and then based on this distribution, I can use the Monte Carlo simulation method I taught in the previous class to actually get the net value for each year. right? We did it for 1 year before in the previous class, for 1 year. Now you can do for year 1, year 2, year 3, and year 4. Use the Monte Carlo simulation method. And then use the present value factor or the present value method I just told you to calculate the net present value. And it's gonna be a distribution, right? Because before what we get is a distribution. So if you do a very complicated exercise, then you get a alpha machine net present value distribution, and for beta machine a net present value distribution. And this is the PDF, right? And if you convert this to CDF, then you can do whatever check for first degree or second degree stochastic difference, as I already told you. Do I need to go back to any part of these? No? Yes.
What is scrap the
It means that basically you at the end you sort of terminate your business and sell out the machine, and what is the remain value of that machine? Yeah. So that's why it only happens in year 4. Yeah. So I was gonna actually go for an application of pricing of risky asset in financial market. So basically this model is called a CAP-M, but so I did this slide a long time ago, but basically now I think it's not that necessary we go through this example. So this is not gonna be in the exam, and it's not even in the textbook, okay? So don't worry that too much. So, are we good? Okay. So now let's go to the chapter 9. So, chapter 9 is about revising judgments in the light of new information. Okay, so we actually we already go through a lot about this before, okay, because we talk about decision tree. And one kind of decision tree or probability tree, the probability or decisions come in sequence, right? So we make one decision first, then we see another kind of possibility of new decision making come in. This is already a sequential process. So, and after you make a choice, you might see new information come in. You either lost money, earn some profit, or something happen. And then based on new information you might make a new decision, something like that. Okay, but now we're talking about a little bit different context. Now is that I'm making a decision now. If I got the initial decision, I might choose, or for example, if I'm doing a decision that I need to constantly do. For example, I choose breakfast every morning between 2 different brands of cereal. Okay, and so given suppose I don't get tired of either kind of them. Okay, so if I simply prefer one to the other, I will simply choose the same cereal over and over every day. But suppose there are some new information come in also every day. For example, about the nutrition content of each cereal, and I'm a very healthy person. I care about that a lot. Or there's some new information telling me that one of the cereal is poison somehow. Okay, so or it's not good for your kids or something. Either way, you might based on this information generally change your behavior or revise your idea about what you should do in your decision-making process. Okay, so revisit the midterm 1 problem. Actually, the coronavirus question I gave there was very much this kind of idea. Okay, so so already go through this. I thought I wouldn't go through this last week, but we did. So basically, you should remember that. So what I mean by new information is that, for example, after you do one test, that gives you some information, right? And after a second test, you get even more information. Okay, so like the question I gave in the midterm, you will revise your probability assign for whether this person actually had the disease or not, based on how many tests he actually went through, not simply by whether the test result is positive or negative. Okay? So the formal term of the theory that we do this kind of calculation is called the Bayes theorem. Okay, how do we get the Bayes theorem? So this is not really a proof, but similar idea. So for any event B, this is B. Suppose he intersect with another event A, then event B can be separated into 2 parts. This is part 1, this is part 2. Part 1 is A intersect with B. Part 2 is A complement intersect with B. Right? So you either is part of A and the B, or you are part of not A and the B. Because not A and the A together is everything. So you must be one of these set. Right? So that's how you get this. So PB equals P A intersect B, and the P plus P of A complement intersect with B. Yes.
Can you just repeat what's the winner C will be A?
Yeah, I know what you're talking about. Yeah. So if this is everything, this is A, the rest is A complement. Cool?
Yeah.
Okay. So everybody clear how we get this? Okay? Now, based on condition probabilities definition, remember that PA conditional on B, actually I want to do B conditional on A. B conditional on A is PA intersect with B. Right? That's the definition of conditional probability. You should recall that from chapter 6. And you multiply this to here. So PA here, erase this. So that's how you get from here to here. P in A intersect B is this one. PA times PB conditional on A is this one. The order is different, but the same thing. Are we clear? Similarly, you can get this one from here. So it's just simply followed by definition. Okay? Okay? Now we consider another. So usually this is what we eventually want to get. PA conditional on B. We already know what's PB conditional on A, but we don't know PA conditional on B. Okay? And how do we get that? So again, by definition, PA conditional on B is this. This is again the definition of conditional probability. And we also know, again from definition, PA intersect with B equals PB conditional on A times PA. This again is from here. And what about PB? PB is here, right? So PB can be replaced by these two things. Goes to here. Then we arrive at the definition. We arrive at the Bayes' theorem's formula. Okay? So basically, all the information you have is PB conditional on A and PB conditional on not A, and the probability of A and probability of not A. Then you can arrive at the probability of A conditional on B, all by definition. So it's simple theorem. But basically what you did in the midterm last question is basically this. Okay? So Bayes' theorem, another view is that you will start with a prior probability. Okay. So Bayes' theorem is like sort of Bayes statistics. That's actually a term. Okay. Bayes statistics is counter to or compared to so-called classical probability or classical statistics. So classic is what basically you learn in undergrad the first statistic course. You usually learn the classic one, or in high school you learn the classic one. In the classic one, we basically assume that the probability is something fixed. Distribution is also fixed. The distribution don't change. In the Bayes view, there's nothing fixed, nothing constant. So you might have a prior probability. For example, a lot of times this is more true because, like I said before, for example, if you enter a stock market, you're predicting the price tomorrow. You don't really know the probability of, whether the Netflix is gonna go up or down, and go up by how much and go down by how much. Right? You don't really know the probability. So what you actually do is you will assume that you know and have a probability distribution that you assume to be true, and that's your prior. And suppose then you go to Google and Google for more news about Netflix, and you might get more information come in, and based on this new information, I might adjust my current prior and get a posterior, a new probability distribution. That's the whole idea, whole picture of the Bayes theorem, basically, or Bayes statistics view. So, suppose you are drilling, you are an oil company that drilling new oil, oil well in some part of the world. Okay, so either gas exists at the location or gas does not exist, right? And because you have basically no idea in the beginning, so your prior is 50-50. There's 50 chance there's gas here. There's 50 chance there's no gas here. Okay? And what you actually do for this kind of company is that you do a test drill. You test it and see whether it does have the gas or not. But remember, the test is not always reliable. Even the test tell you there's no gas. It might be because the exact location you drill down is incorrect. Okay, and even if it tells you it has gas, it only means that this exact location has gas, and you don't know how much. What do you mean by this location actually has gas? It means you need to have enough gas for you to be profit, right? Actually, a lot of the oil well or gas well right now in the world, people know there are gas or oil there, but the price of gas and oil is not high enough. So there's no profit here to spend that much money or either manpower or infrastructure or machine, transportation costs to actually drill down and get those oil or gas. So even if the testing indicate there are oil, it's not a 100% true case. Okay, so suppose the test is actually quite easy, quite symmetric, like the coronavirus test I gave in the midterm. So it's symmetric. So if it actually has gas in this location, there will be a 95% chance that the drilling indicate there are gas. That also means there is a 5% chance it will indicate there's no gas. Okay? And if there actually no gas, there is a 5% chance that the drilling will indicate there are gas. Okay? And so after this one drill test, my prior will be changed. My prior will become a posterior. And exactly by the method you guys should already know. Okay, so if the drill indicate there are gas, then there are two cases. One is that you go through this pass. One is this pass. And the probability, are shown here. So this times this becomes this. This times this becomes this. And overall, this is 50% chance, right? Overall, there are 50% chance. So 50 of 0.475 and 50 of 0.25 are 0.95 and 0.05. So that's the posterior probability you get if your drill indicate there are gas. Since this is a symmetric case, I can actually also tell you, you can also, don't you actually do the calculation, you can easily see that if the drill indicate there is no gas, then the posterior probability that this place actually have gas is 5%, and no gas is 95%. Everything's reversed, basically. Okay? Are we clear? Okay. So we call this 95%, the reliability. Reliability. So we want this reliability to be as high as possible, right? By the way, this is actually a symmetric problem. So a reliability of 1 or 100% is actually equal to a test of reliability of 0%. Why?
Because if there are exceptions, we don't know it.
Because what?
If there are exceptions, we don't know it.
We what? So this is like if you're gambling for, say, for a ball game, and you follow this YouTuber. If this YouTuber always correctly predict the winner of the ball game, that's good for you, right? You follow this YouTuber and you just, put a lot of money on the gamble and you win every time. But if this YouTuber sucks a lot, he always get it wrong, then what would you do? Yeah, bet the other side. And you will always win as well. So that's why a reliability of 0 and reliability of 100 is like that.
Yeah, only there is two choice.
So here is also two probability, right? Either there's a guess, there's no guess.
Yeah.
But even if that's not a trait, this idea can be generalized to more cases as well. That doesn't affect the idea. So, but here there's only two. So either it's gonna be positive or negative. That's why we can define a thing called reliability.
Yeah, but this statement is not possible if there is more than two possibilities.
We have a different way of defining what's reliability there. That's a totally different story. Yeah. So you get what I mean now? Okay. So before we have a case of a reliability of 95. That's this line. What this graph is show is that suppose you have before we have a prior of 50-50. So we have a prior of 50. Then after a 95% reliable test, I will arrive at a posterior of 0.95. So this exercise become just 1 point here. Okay? And if you change the prior 50-50 to something other than 50-50, either increase it or decrease it, you will get different posterior. This number will change. And different number will give you different points, and then you can draw this whole line. That's how we draw this one line. Okay? Okay? And this is for 95 reliability. So, but if we do for a 70% reliability, we can draw a different line. That means you change the probability here, 95 to 70. Then you can draw a different line. And actually the worst case, this case you don't even need to do any calculation, okay? So the 50% reliability test must be a straight line. A straight line means what? A straight line means your prior or equal to your, and the slope is 1, by the way. It's not just a straight line, the slope is 1. That means your prior equal to your posterior. Always equal to posterior. That means what? The new information doesn't change your prior. That means it's not helping you at all. Why do people understand why I say I don't need to do the calculation? I don't even need to do the calculation. I can arrive at this yellow line. Why is it straight and slope 1? Is it clear to you guys? Come on, after this we'll have a break.
Linear or it's always stable?
But what I'm saying, why it is linear. Why I say that I don't need to do the calculation. So
Because
it's in the middle. Why is the 50-50? So why is the reliability of 50 always give you no information? Or if I say it this way, it might be
because
easy.
it can either be 50% correct or 50% incorrect, so it's the same every time.
Yeah. I think you guys get the idea. But the key point here is that because there's 2 events here, either it has the gas or no gas. And if you flip, you basically, what it means by here is that this test equal to flip a coin, right? This test equal to flip a coin. Either way, it's 50-50. So it's not helping you make any new judgment, basically. Okay, so we'll come back at 3. Fixed call 不用啊 ，fixed call 你看最低是100嘛，然后最高是300，它就是介于。
可是这样的话，不是应该花100跟300？
画错了，我看一下。看一下有没有任何东西是画对的。
好像那个数字都对不上。
我想一下哦 ，profit 跟 fixed cost。好吧，因为这个图其实不是很重要，然后我当初其实也没认真看过它这个到底怎么画。Tornado diagram 应该是它有一个特殊的画法，课本应该有讲，只是说实在我觉得没那么重要，我就没有认真看。对。
那老师为什么刚刚要特别讲这个字？它是有用在哪里？
没有，就是告诉你说这个表就是可以怎么用嘛，就是其中一个用法是可以算这个东西。
好，谢谢。那我问最后一个，
好，
就是这个的话，它意思是说，就是虽然它可能以时来说 P 的几率比 Q 大，但是仍然 Q 因为
这不是几率哦。
这个不是加总的。
这是加总的几率，但不是几率。加总的几率跟几率是两个不同的东西。对。好，所以在10这个点，它比它大的意思是什么？意思是到10，就是说，以 product P 来说，它拿到的 profit 是小于10的机会，是一半的机会。
哦，我以为是这点的机会还是0.5。
那就是 CDF， 那不是那就是 PDF， 那不是 CDF。一定要分清楚 CDF 跟 PDF 的差别，统计学就是对。
好，我知道了，谢谢。
好。
Quoi?
Soit ici, soit nouvelle Calédonie. J'ai un stage de 2 mois à faire.
Obligatoire?
Et j'ai pas eu de vacances depuis le lycée. Chaque fois on a des stages, des trucs.
Non, c'était tous les ans, on devait pas mal bosser. En fait, tu fais des ans comme ça.
Ah, ça va.